So, I will continue from my last lecture where I was speaking about the autocorrelation method. So, the autocorrelation method is fine. It can give you an idea of the full width half maximum of the pulse, or say the length of the temporal pulse, but it does not really give you the shape of that pulse. I have made a guess of the Gaussian and then gone ahead, but all the time your pulse need not be Gaussian, or it need not be a regular shape like either a Gaussian or the sec h square or a Lorentzian, which all are well mathematically you are able to depict them. It can be a very odd shaped pulse. Then what do I do? Then this autocorrelation technique has to be refined in some way. So, in this diagram what I show you is, suppose this is the intensity of any pulse in time. This is the time axis and this gives you the intensity. So, if you can see, I have two different pulses, one shown in this bluish purplish and the other one is this red pulse. They are slightly different from each other, okay. You can see that. But then when I take the autocorrelation of both the pulses, it will look identical, it will look like this, nice looking simple symmetrical pulse. And so, from this I can only judge the full width half maximum of this pulse from the full width half maximum of this pulse. But I am really not getting these peaks, this shape, this it's not reflecting here at all, okay, in my autocorrelation pulse. So, in fact they look like two identical pulses. So, there is a limitation to this autocorrelation technique. The intensity of the autocorrelation doesn't, it gives a very simplistic intensity. However complicated may be your pulse, the more complicated you will get a very simple profile in the end. As the intensity increases in complexity, the autocorrelation actually becomes simpler. It remains simple. Now, the direction of time ambiguity for all autocorrelations. Okay. There is a time ambiguity, see this one on this direction of the time, it is not symmetrical, basically it is not symmetrical, but you are getting a output symmetrical pulse. And the need to multiply shots for a autocorrelation trace. Okay. By this what is meant is what I said before, that if you have multiple shots, then only you can take this autocorrelation trace. This is the autocorrelation trace. Okay. So, or you need a repetitive rate beam of light. Okay. That may not be possible always. After amplification where you have only one pulse which is amplified, you have to somehow find the shape and length of that pulse with that one single pulse. Okay. So, you should be able to get rid of this multiple shots, okay. And also to get a full width half maximum, we have made some kind of a guess. See here, we have made a guess of that Gaussian pulse. So, in case of a Gaussian pulse, it is 1.41 times larger, the autocorrelation pulse. In case of sec h square, it is 1.54 times larger. This you can derive just like I have derived before. 1.41 means that root, it comes out as a root. Okay. So, in case of Gaussian and sec h square, you have you have a different multiplication factor for your full width half maximum. But then sec h square pulse is also a very symmetric pulse, Gaussian is also a symmetric pulse. So, if we make a guess of a Gaussian pulse, it is okay, you can go back to the original. But a pulse like this you can you cannot make a guess as a Gaussian pulse. So, what can be done? Something has to be done. Okay. So, there are certain conditions on the second harmonic generation crystal. See, there are some more, I mean, it does not work out just that easily. It should, the second harmonic generation crystal should support that bandwidth. Ultra short pulses means bandwidth is very large. So, all those your second harmonic generation crystal should support that in the sense it should be for each of those frequencies it should be able to create double frequency. Okay. That is what I meant by support. Okay. So, it is not as though some of those frequencies will be absorbed or cut off or reflected off, it should not be like that. Okay. All those frequencies should be able to pass through your crystal and create the second harmonic generation with its bandwidth. Some of the second harmonic generation crystals used are BBO, beta barium borate, KDP, potassium dihydrogen phosphate. You have come across this, I have spoken to you before about this, and then lithium niobate. Okay. So, you already know these crystals. Now, all these crystals do give a very large bandwidth, do support the large bandwidth of a femtosecond level pulse in the wavelength of 1.06 and some other 800 nanometer also, it does support that bandwidth. So, these crystals have become very popular in its use. But what about some other wavelengths? What about some say in the far infrared 10.6, a carbon dioxide laser? Those crystals will be different from these. Here they are mainly in that near infrared region, lasing action. So, those crystals will be different, and then it has to support the bandwidth. That is the biggest idea. If it does not support the bandwidth, the very pulse that you are trying to measure, okay, you will get a wrong measurement, because frequency is a big part of these short pulses. The moment some of the frequencies are not measured properly, you are not getting the pulse length also. And then another problem in this is the crystals are all materials. So, when these short pulses pass through some material, you know there is positive GVD. That means there is dispersion. Group velocity dispersion comes into the picture. The shorter the pulses, the larger the bandwidth, and so larger the group velocity dispersion. And group velocity dispersion, if you remember in my previous lectures, gives rise to a longer pulse. So, again you have distorted the pulse within that crystal itself. Okay. So, what you need is, you need a very thin crystal, so that it does not distort your pulse too much. Thin crystal, they are in mm thickness, 1 mm thickness, 2 mm, 3 mm, okay, and then you have to tolerate that. So, your estimate of the pulse is also dependent on the thickness of your crystal, so that you avoid the group velocity dispersion that marks the shape of your pulse. Okay. So, and also you need to have a big crystal. By big means big in diameter, to avoid clipping. Basically, there has to be a spatial overlap, as you have seen before. So, this diameter, suppose it is a circular crystal, it is big, but it is thin. This shaded part, it is very thin, but this diameter is large. Diameter is large, so that the two beams can overlap nicely in the crystal. See here, these two beams should be able to overlap nicely here on this crystal. And the moment these two beams, which are coming at an angle and they are in fact passing through a lens, they have a big divergence. The moment after the focal part of the lens, they have a big divergence. So, all that should be captured within my crystal. So, if this crystal is large, you are not missing out on the peripheral parts of the beam. Okay. So, since the whole process depends on the intensity detection, you can't afford to miss even spatially any part of the beam. If you miss spatially, there also you have made a distortion in your time in the temporal part of the pulse. Okay. So, these are the difficulties of the autocorrelation technique, of the intensity autocorrelation technique. But then luckily some relief exists, that is you can measure the shape of the pulse, the phase of the pulse. If you take its spectrum, remember we took Fourier spectrum, Fourier inverse spectrum. So, the time and the spectrum, they are correlated with each other. So, delta t delta nu is equal to some factor, say 1. So, delta t is inversely proportional to delta nu. So, you do get an idea of your time if you have some idea of the spectrum in that pulse. So, that is what we are going to do now. Okay. So, this technique is called FROG, frequency resolved optical gating. Okay. So, you are trying to resolve all the frequencies which are involved in this pulse. You are trying to threadbare look into all those frequencies, each of those frequencies. Okay. And optical gating, because you are gating it with another pulse. I will tell you what is meant by gating. That means you are taking small parts of the pulse and taking its frequency spectrum. Okay. So, this system is exactly like the other one. The only thing is the second harmonic generation here, it does not go to just a photodetector, it goes to a photodetector, but at the same time it also goes to a spectrometer. That means you are analyzing your double frequency generation or the green light, which I have taken as an example. You are taking the spectrum of that as well as the intensity. So, all you have done is, everything remains the same, all you have done is added one more spectrometer. Okay. So, here the pulse that is to be measured enters here, there is a beam splitter here, part of the beam goes here, another part of the beam comes here, okay. And ET as before, electric field of the light, and this ET electric field of the light after certain delay tau, and you can adjust your variable, the delay here, variable delay tau, okay, tau is your delay. It goes through a lens, it focuses onto a second harmonic generation crystal, it creates 2 omega frequency and then it comes out. And these two beams are to be missed out, we are not bothered about the green light that is that has been caused because of these two beams separately. We are bothered about the green light that has been caused when these two pulses or these two beams are correlated. That means they overlap in space and in time. space and temporarily. So, when that happens, we are only bothered about that. Otherwise, there is no way of measuring it. And here, frequency resolved optical gating. Optical gating means they are calling this ET minus tau pulse as a gate pulse. It's just another way of putting it. Both of them overlap slowly, but you are gating this pulse with the help of this pulse. You allow only this part, the overlap part, to give you a intense second harmonic beam which is detected. So, this is acting like a gate. Okay. So, it is just a name, basically these two have to overlap just like in the previous case. And the only difference between the previous case and this case is you are also measuring the spectrum of this green beam which has been created in this overlapped part. Okay. So, this is the overlap part and we are seeing this, and I just show it in color because we are interested in the spectrum of this beam. So, now what happens, and I have written the field amplitude here like I told you before, it is not the intensity, it is E, the ET and ET minus tau field. Now, what are we creating? The electric field of the ultra short pulse can be written as that AT e to the power I phi t. Okay. If you notice, I have introduced a amplitude part and a phase part. Any pulse can be described completely with an amplitude and with a phase. Then the description is complete. Okay. So, with this attempt, I want to make a measure of my measure of the shape of that pulse. So, I have AT, which is an amplitude which is changing with time as it goes, and then I have a phase also phi. Okay. In frequency domain, so this is in the time domain. In frequency domain, all I have to do is take a Fourier transform. So, E omega, the frequency domain of this, is equal to E t e to the power minus I omega t dt. Okay, this is the Fourier transform. So, the same pulse I must have in my in the spectral domain too. Okay. So, I am measuring the pulse in the spectral domain also with this spectrometer. With second harmonic generation, the signal electric field is EC, signal electric field, that is the final signal which you are analyzing, that is why it is called E signal, T tau. That means it will, the signal of the second harmonic generation depends on tau, the delay, and depends on the actual time. Just like before, even this is the one. Now, this is the convolution or the correlation, these two are correlated, okay. And it is auto-correlated, remember, because the same pulse is correlating with that on its own. So, it is auto-correlation, that is why it is auto-correlation. So, by this I get my the correlation between the two pulses. Tau is the delay between the split pulses, this you can understand. Now, what am I measuring now? An extra thing, the spectrogram or the Fourier transform of the nonlinear signal field. Okay. Nonlinear because I have added a nonlinear second harmonic generation crystal. So, my signal field is the field of that nonlinear signal, that means of my second harmonic generation signal. How do I describe the spectrogram? The spectrogram given by omega tau. Omega is the spectrum, the frequencies, and tau is of course the delay time. Okay. That is given, now it is the intensity that it is picking up. It's picking up the different frequencies in this pulse, and also it is taking the intensity of that. So, this is what I get. Okay. So, E signal T tau, basically I am taking a Fourier transform. if I take a Fourier transform of my green signal, E signal t tau, e to the power minus I omega t, Fourier transform, I take that and I take the square of that because I am looking at the intensity. So, S omega tau is called the spectrogram. Okay. If you see in this curve, it is basically doing the same thing as before. So, my delay, variable delay can go between 0 and tau. Okay. So, slowly this is overlapping more and more with this, more and more with this. It completely overlaps and goes on the other direction. And for each point like this, for this much overlap, I take the spectrum, I take the intensity. It overlaps a little bit more, I take the spectrum, I take the intensity. It overlaps completely, I take the spectrum and I take the intensity. That is how I get all these points which I require between 0 and tau. Okay. Okay. So, this is my, why is it called a spectrogram? It is not called a spectrum. We are measuring the spectrum, but it is called the spectrogram. Spectrogram because actually there are it is like a 3-dimensional thing. On one axis, I have the delay time. On the other axis, I have the frequency, and in the center you can have the intensity. That can come on in a third direction. Okay, so I am measuring actually the frequency. I am keeping a measure of the frequency, I am keeping a measure of the tau, which is the overlap from here, and I am measuring the intensity of that particular frequency also. Okay. So, all these three things I am measuring: frequency in the spectrometer, tau from the length traveled by length changed by these two mirrors, and intensity also in the spectrometer, or there can be another detector. So, what does my spectrogram look like? Not a spectrum, but the spectrogram. So, here I give the spectrogram of a wavefront ET. This is my spectrogram. These two are examples of a spectrogram. See, this is the delay time. This is the wavelength or frequency along this axis. I have not shown the third axis, but the third axis is actually the colors on this 2-dimensional map. Okay. So, this is the intensity gradient. Blue gives very high intensity and red gives low intensity. Okay. So, this is not the spectrum. This red and the blue, it is not the frequency. The frequency is there along this line. You know, you can get the different frequencies. But these blue and this red and this yellow, that is giving you the intensity. So, for this particular frequency, say somewhere here in the center here, it has the highest intensity. Some frequency here, it does not have such a high intensity. Some frequency in this region has very low intensity. So, maybe that pulse has just gone down completely. So, the center has the highest, the peak intensity is in the center, and the peak intensity is for that frequency, that particular frequency here. Okay. So, this is one spectrogram. Another spectrogram could be this. It's a different shape of a pulse, that is why these spectrograms comes into the picture, and sometimes there is a chirp in the pulse. So, it also shows that there is a chirp in the pulse. Try to recollect what I said about chirp. Chirp means the frequencies have spread out over the pulse length. It could be that some amount of chirp, but even otherwise you can get a spectrogram like this. This is just as an example. Okay. Now, the spectrogram here I have written that again, ET minus tau, okay, e to the power I omega t. That is because here E signal T tau I have just replaced over there with this E signal T tau is that. Okay. So, my spectrogram consists of ET minus tau and e to the power I omega t dt. Okay. So, you can see there is this part is the correlation part in my second harmonic generation and this is the phase. So, within this spectrogram is embedded my phase and the amplitude and some relation to the time. Okay. So, this spectrogram is a very important thing. The spectrogram yields the spectrum frequency or wavelength and intensity of ET with time or delay tau. Now, I have to do a phase retrieval program for to get back the shape of the pulse. Okay. So, I will tell you what exactly is that phase retrieval part. It is called phase retrieval or deconvolution. Okay. And this trace, this is called the spectrogram or it can be called the frog trace. Frog trace or the spectrogram is S omega tau and it is an experimentally collected data. So, you have collected all this data experimentally as I have showed before. You have collected the spectrum, you have collected the intensity and you have collected the delay time. So, in my next lecture I will tell you exactly how you can deconvolute this information that you have gathered to get to your original pulse that you started with. The original pulse that I started with is ET. This you have spectrally experimentally measured. So, within this is embedded something about your pulse, but you have to deconvolute it. You have to find a way of coming to this value from your experimental value here. I will talk about that in my next lecture.